Let's go deeper into Hadoop's MapReduce implementation. As the name implies, there are two phases to MapReduce. There is the map phase and the reduce phase. The first phase in a MapReduce program is the map phase. The map, or mapper's job, is to create or process the input data. As shown in the diagram, this is usually a file or directory. This file is stored on HDFS and is passed into the mapper function. The file is usually passed in line by line into the mapper function. The mapper processes this input data to create as few or as many outputs as needed. There is no API contract requiring a certain number of outputs given the input data. This is completely up to the programmer. The mapper's output is then passed to the reduce phase. The reduce or reducer's job is to process the data from the mapper into something usable. Every single value from the mapper is passed into the reduce function. The reducer will create new output values based on the input from the mapper. The new output values from the reducer will be saved to HDFS. There is another part to MapReduce that the API gives us. The technical name for this part is Shuffle and Sort phase. I prefer to call it the magic. We'll talk about what happens during this magic part later on. As I mentioned in the introduction, we're going to use playing cards to understand MapReduce. You might be familiar with standard playing cards. I like using cards to show MapReduce because the cards have colors and shapes for suits. The pack has 4 suits: spades, hearts, diamonds, and clubs. There are some other cards that aren't from these 4 suits that are the jokers. I strongly encourage you to follow along with me as I do the exercise, or watch me do the exercise and then do it yourself. Either way, you'll understand the concepts by moving the cards around with your hands and for yourself. Playing cards have 4 suits: spades, hearts, diamonds, and clubs. Looking at the cards, we can see that some of them have numbers and others don't. Those cards are the ones like the ace, king, queen, and jack. We also have joker cards in the pack. We're going to pretend that non-numeric cards are bad data or data that we want to exclude. We're simply going to ignore them and throw them out as we find them. Our goal, or program, is to add up the card numbers for a single suit. This will give us the sum of the numbers for a particular suit. We're going to be acting like a Hadoop cluster. I have a 3 of diamonds. That's numeric, so I'm going to keep that and place it in the diamonds pile. We have a jack of spades. That's non-numeric, so I'm going to throw that out. We're pretending that this jack is bad data that we want to exclude. We have a 3 of hearts. That's numeric, so I'm going to keep that and place it in the hearts pile. We have a 2 of hearts. That's numeric, so I'm going to keep that and place it in the hearts pile. We have an ace of hearts. That's non-numeric, so I'm going to throw that out. We have a joker. That's non-numeric, so I'm going to throw that out. I'm going to speed this up now and quickly sort the remainder of the cards. Queen of diamonds, 3 of spades, 6 of hearts, 10 of spades, 8 of clubs, 7 of hearts, 4 of spades, 6 of diamonds, 3 of diamonds, 8 of hearts, 7 of diamonds, 4 of clubs, 7 of diamonds, 9 of spades, 7 of clubs, 5 of spades, 10 of diamonds, king of diamonds. Looking at our result, we have 4 stacks of cards. Each stack makes up 1 suit's worth of cards. Remember that our objective here is to sum up the card numbers for a particular suit. It's much easier now that we've sorted them into piles that are only made up of that suit. We can just pick up that stack of a suit and know we hold all of the cards for that suit. From there, we start summing things up. Our algorithm is pretty simple now because we've separated things out. We've manually done what would be done in MapReduce. We do this by going through data and saying this piece of data is of a particular type. In our case, we've said that the card suit identifies the type of our data. We'll see in a minute why that typing is so useful. Hadoop wouldn't be getting any notoriety if it can just process a few playing cards. It needs to be huge amounts of playing cards. Hadoop handles these massive amounts of cards by distributing the load across multiple nodes. Let's see how Hadoop scales using playing cards again. I'm holding a stack of playing cards. I have two pieces of paper representing two nodes running together. On the left is node 1, and on the right is node 2. I'm going to take the cards and split them in half. One half will go to one node, and the other half will go to the other node. Even though I'll be doing the algorithm one at a time, both nodes are running simultaneously. I'm going to run the same algorithm as before. I'll simply take my node stack of cards and sort them by suit. Now, I'm going to run the algorithm on the second node's cards. Looking at things, I have two nodes with 4 stacks each of cards. Remember that MapReduce has two phases. There is the mapper phase that we just did. Now we have to run the reduce phase. Do you remember the magic part of MapReduce that I spoke about earlier? I'm going to manually perform part of that magic. I'm going to combine the club's cards from both nodes on node 1. Next, I'm going to combine the diamond's cards from both nodes on node 1. Then, I'm going to combine the heart's cards from both nodes on node 2. Finally, I'm going to combine the spade's cards from both nodes on node 2. Let's look at what this magic has done before we continue. Node 1 has a stack of every club's and diamond's cards in separate piles. Node 2 has a stack of every heart's and spade's cards in separate piles. This magic has allowed several nodes to process data independently and combine it together. This magic combined the data from all these nodes so that a single node can process the entire suit at once. This is how a Hadoop cluster works in real life. The cluster is made up of tens, hundreds, or even thousands of nodes, all connected by a network. A job is broken up into smaller parts to run on each node. These smaller parts are usually based on the amount and size of the data being processed. The mapper on a node operates on that smaller part. The magic takes the mapper's data from every node and brings it together on nodes all around the cluster. The reducer runs a node and knows that it has access to everything with the same key. Let's imagine a stack of playing cards that goes all the way up into the stratosphere. There are two problems with this scenario as we scale it that high. One problem is storing that many cards. Remember that Hadoop breaks up the data into smaller parts. What would happen if you were to take a section of cards from the bottom of the tower? The entire tower of cards would fall. You'd really want to break up the single, very tall tower into lots of shorter towers. That way, you could work on them much easier. Hadoop does the same thing. We talked briefly about HDFS as the distributed storage mechanism. Let's say we were to store a terabyte file in HDFS. That file would be physically broken up into much smaller chunks. By default, these chunks or blocks are 64 megabytes. Often it's recommended that these blocks be 128 megabytes. The file continues to be logically 1 terabyte in size. We get several benefits by breaking up the terabyte file into smaller blocks. When a mapper is operating on a terabyte file, it's actually operating on a block and not the entire file. The terabyte file is being worked on by various nodes in the cluster all at once. The various nodes are just operating on different chunks. Once the mappers are all done, the magic takes over. All of the data in the terabyte file is combined based on the key. The reducers run on different keys. We have a big benefit that comes out of breaking up a problem this way. We're able to efficiently break up even a large file into smaller pieces. Having 10 nodes running on chunks of the same problem is much more efficient than a single node running the same problem. Hadoop scales in virtually a linear fashion, and it would take about 1/10 the time a single node would. Hadoop's ability to scale sets it apart from other systems.